The factors vanish at 2 and 3.
Watch the scene first. The math is built into the world, so the quantities can be seen before they are named. Here, in moon-pond parabola, moonlit arcs move across the pond, but the specific spots where they touch the waterline are difficult to pin down. To find those exact coordinates, we solve quadratic equations in one variable. The values and symbols required are carved into the physical terrain. The environment shows the relationship, and the notation records it. Examining the algebraic structure of the equation determines the most efficient way to see where the arcs meet the water. Tella reaches the first reflection pool, where the arrangement of stones along the bank shows the equation, x squared minus 5x plus 6 equals 0. Because this structure is simple, we can separate it into two groups. X minus 2 times x minus 3 equals 0. Since the product is 0, we set each group equal to 0. This isolates the values, showing that x must be 2 or x must be 3. The landscape shifts as the calculation is finished, showing how factoring works when an equation breaks down easily. The solutions are x equals 2 and x equals 3. Tella moves to a new island obstacle with a different structure. X squared plus 6x plus 5 equals 0. To solve this, we complete the square by moving the 5 across the equal sign, leaving us with x squared plus 6x equals negative 5. We add 9 to both sides to balance the equation and create a perfect square on the left. X plus 3 squared equals 4. Taking the square root of both sides removes the exponent, leading to two possibilities. X plus 3 equals 2, or x plus 3 equals negative 2. Subtracting 3 from both sides isolates our final values for x. Reorganizing the equation provides a path forward when simple factoring fails.
The quantity x plus 3 squared equals 4. So x is negative 1 or negative 5.
The solutions are x equals negative 1 and x equals negative 5. The terrain becomes more jagged as Tella encounters a vertex island representing 2x squared plus x minus 3 equals 0. For equations that resist factoring and simple reorganization, we use the quadratic formula to find the exact coordinates. We identify the variables a equals 2, b equals 1, and c equals negative 3, and place them into the formula. Simplifying the values beneath the square root and the denominator gives us negative 1 plus or minus 5 divided by 4. The formula provides a solution even for the most complex initial structures. The solutions are x equals 1 and x equals negative 3 halves. Tella reaches the final shore, where the arcs meet the land. We can now see how the solutions to x squared minus 5x plus 6 equals 0 relate to the graph of y equals x squared minus 5x plus 6. Tella can see that the arcs only meet the shore at the water's surface, where the height is 0. In the coordinate system of the pond, this means the output y equals 0. On this coordinate plane, the points where height is 0 are the x-intercepts, the locations where the curve crosses the horizontal axis. These intercepts align exactly with the algebraic solutions we found, x equals 2 and x equals 3. These intersection points on the bank correspond to the solutions calculated earlier. They appear as the x-intercepts at x equals 2 and x equals 3. By following the structure of the equation, we find the exact numbers that define this environment. The landscape of moon-pond parabola is now clear. Algebra is a language that maps the geometric and physical patterns of the world around us.
The quadratic formula gives 1 and negative 3 halves.